Hello and welcome. My name is Lisa Stewart. I use the pronouns she, her, hers, and I am Chief Administrative Officer at the Kavli Institute for Theoretical Physics, also known as KITP. We are happy to welcome you to today's 12th seminar in the Innovate Seminar Series put together by the National Society of Black Physicists. And KITP hosts this talk series. Today's talk will be presented by Caleb Levy, who is a student at Colgate University, sorry. And all the prior talks are also posted on both the NSBP and the KITP websites. So you're welcome to find some of our previous speakers as well. Today's talk will be approximately 30 minutes. Followed by 10 to 15 minutes of moderated Q&A. Please put your questions into the Q&A box at the bottom of your screen, and then we will address those at the end. Next up, I'd like to introduce you to Farah Simpson, who is a leader of the NSBP Student Council, and she will tell you a bit more about this Innovate Seminar Series. Thank you.
Hello, everyone, and welcome back to the NSBP Innovate Seminar Series. My name is Farah Simpson, and I am the current student representative on the board of the National Society of Black Physicists and leader of the Student Council. The Student Council and the board of NSBP, we are responsible for this series, and KITP is the host. So thank you again to KITP. We really wanted to create this series, especially for not just our professionals, but also our student members, so that we could really be able to engage with each other's research and be able to share our research ideas in a non-specialist way. This is a very special talk in our series because we selected winners for the talks at the NSBP conference, and Caleb was one of those winners. And his talk was incredible, and we cannot wait to share it with you here today and share it with a wide audience. And the purpose of these series is really to provide that wide audience for our NSBP members to get exposure and also be able to hear the research ideas of other members within NSBP. And so we are excited to have you, Caleb. Now I will introduce you to the president of the National Society of Black Physicists, Dr. Stefan Alexander.
Thank you, Farah, and it's great to be here with everyone. And yes, this is a great pleasure to introduce our speaker, because the big part of this speaker series is to really expose all the great research across the board in NSBP land. And so on that note, I want to introduce our speaker. I had the great pleasure of actually speaking to Caleb maybe a year ago, because my PhD student who's graduating this year, Leah Jenks, also went to Colgate, and I was very impressed. And lo and behold, he wins our great award. And so let me just say a few things about our speaker. Caleb Levy is a junior physics student at Colgate University who was born and raised in Kingston, Jamaica. Caleb currently works with Dr. Cosmin Ilie at, and correct me if I'm mispronouncing Cosmin's last name, at Colgate on dark matter phenomenology and astrophysical objects. And he hopes to study theoretical cosmology and particle theory, which is actually what I work on, after graduation. Caleb is also an avid music lover. He's currently learning jazz piano, just like the great Monty Alexander, the great jazz pianist from Jamaica, and also Cedar Walton, who played with Miles Davis, was also a great Jamaican jazz pianist. Check his stuff out, it's amazing. He's an amateur tennis enthusiast and a lover of dogs. Caleb, the floor is yours.
Thank you so much for the introduction. And thank you to NSBP for this opportunity to speak today about my research. Today, I'll be talking about some research that I have done since my freshman summer at Colgate with Professor Cosmin Ilie. And this work was recently published in Physical Review D. I've also just put a little QR code if anyone wants to scan quickly and look at the original work on archives. Okay, so I just wanted to start out with a little bit about me before jumping into all the physics. So as Stefan said, I was born and raised in Kingston, Jamaica. I left for Colgate when I was 19. And for those of you who don't know, Colgate is in central New York, and Jamaica is a tropical island. So before coming to Colgate, the coldest weather I think I experienced was probably in like the mid 50s Fahrenheit, and that was like really cold for me. So coming here was sort of a big shock, because now I dream of days when it's 50 outside around this time of year. So that was a big adjustment. Actually, in this picture was taken like last week. I went up to New Hampshire and I did some winter hiking with my aunt, which is probably like the least Jamaican thing I could have done coming up here, going out into the cold on purpose. But it was really fun. So very different, but really fun. Another big part of my identity is my love for music. I didn't really discover this until I left high school and took a gap year, and that's when I started like getting into the piano and stuff. And now I'm learning jazz piano, which is very, very fun, but also very challenging. But it's great to have something outside of physics that sort of stimulates my mind. I also have a dog who I miss very much. His name is Mr. Baggins. He's named after Bilbo from Lord of the Rings. And you can ask any of my family members. The first person that I ask for when I call home is Mr. Baggins. And yes, it wasn't a mistake. He is a person. I also just wanted to give a little shout out to some of the people who have really helped me in my journey so far and have helped me grow as a physicist. So Professor Ilie, of course, my advisor, Jacob Pilawa, who he was a senior when I first got to Colgate and actually tutored me. And then we ended up collaborating on some other work, which was really cool. Jillian, who I still work with to this day on this kind of research. Sayong, who weirdly enough I've never actually met in person because he graduated before I left, but we've collaborated as well on this kind of research. Okay, so this is kind of just a brief outline of the physics part of the talk. So I'll just start with a brief introduction on dark matter, and then I'm going to discuss a little bit about the formalism that is used for calculating the rates of dark matter accumulation in objects. And I'll specifically focus on how we extended this formalism to account for different scattering targets in objects. After that, I'll discuss the possibility of placing bounds on dark matter properties using the observation of population 3 stars, which are the first stars in the universe. And finally, I'll end with some closing thoughts. Okay, so what is dark matter? I have no idea, and if anyone in the audience does happen to know, please feel free to jump in and enlighten all of us. The first mention of dark matter is typically dated back to the 1930s when Fritz Zwicky measured the speed of galaxies in clusters. And basically what he found was that if we estimated the total mass of the cluster based on the amount of light that was being emitted from the different galaxies, and we compared it to the mass that should really be there because of how fast these galaxies are moving, there was a pretty big discrepancy. So the most natural explanation, which is the one that Zwicky put forward, is that there must be like a missing matter component that is not visible, hence dark matter. Since then, there's been a plethora of evidence pointing towards dark matter, and to the point where most physicists would say that its existence is pretty certain, despite not knowing exactly what it is. So some of this evidence includes flat rotation curves of galaxies. And this was work that was pioneered by Vera Rubin and Ford. And this implied that dark matter actually is not just on this cluster scale, but also on galactic scales. Some other evidence is that if we look at distant galaxies, a lot of the times we see them being lensed by mass in between the galaxy and ourselves, like we see in this picture. And because of general relativity, the light coming from the galaxy ends up bending and warping into interesting shapes. And so this implies that, in these galaxy clusters, that there is this like huge missing matter components. And this actually can be used to map out like the dark matter in galaxy clusters. Another big piece of evidence is the cosmic microwave background, and this actually measurements of sort of little temperature fluctuations of the cosmic microwave background have provided some of the most precise predictions of the amount of dark matter in the universe. Okay, so I think I hopefully fully convinced you that while we don't know exactly what dark matter is, that we do know that it exists. So what else can we say about dark matter other than it exists? So one thing is that we know that it makes up about 85% of the mass budget of our universe. So that means that all the regular matter that's on Earth and stars, galaxies, asteroids, other planets, etc., that makes up only 15% of the total matter in our universe, and the rest is still unknown. We also know that dark matter interacts very weakly, if at all, with normal matter. And I'll talk about this a little later, but experiments on Earth have really constrained how strongly dark matter can interact with regular matter. And this is through a quantity known as the scattering cross-section. And this is just basically a measure of how strongly coupled dark matter is to the standard model. And they've essentially found that for the most popular dark matter models that are put forth, that they have to interact quite weakly, or we would have seen them in the lab by now. Another big thing about dark matter is its role in the formation of structure in our universe on all scales. So because dark matter interacts so weakly with normal matter, it was the first to collapse in the early universe. And essentially, it's believed in like the current model that it is dark matter that provided essentially the gravitational seed that allowed regular matter to collapse and form like the first stars and galaxies. And this is actually very relevant to the work that I'll be talking about, because in this work we're studying the first stars in the universe, and they're thought to form in these very dense dark matter halos, which are essentially just clumps of dark matter. So I just wanted to talk about some of the ways that physicists have been trying to detect and constrain particle dark matter candidates. And some of the methods include direct detection, and this is where we hope to essentially measure very small energy deposited, the very small energy deposited by dark matter that transits Earth. So the particles go through Earth, go through our detectors, and if they interact with the stuff in the detectors, they'll provide a small recoil. Up to date, none of the direct detection experiments have a confirmed detection, and so the best that they're able to do is place a constraint on how strong dark matter couples to regular matter, which is what these lines represent. So everything above these lines are excluded by the different experiments, because if dark matter did exist in these regions, we would have seen it. We also have indirect detection, and this is when signals from dark matter annihilations elsewhere are picked up by like our telescopes. We also have particle creation, and that's basically the hopes of producing dark matter particles in the lab with particle accelerators and colliders. And then another way to constrain dark matter candidates, and this has become a very popular way, is through observables from astrophysical objects. So dark matter could interact with these bodies, and it could be stars, exoplanets, white dwarfs, neutron stars, and it could have consequential effects on the object's evolution. And so there could be some observable features, basically. And by measuring these objects and getting lots of data on these objects, we can either hopefully find dark matter or at the very least constrain. Okay. One thing I just wanted to quickly mention is this yellow region here, and this dashed red line is what's known as the neutrino floor. And the idea here is that if when these direct detection experiments increase their sensitivity to the point where they can start to detect neutrinos in large amounts, it'll be very difficult to detect a dark matter signal as different from a neutrino signal. And so it's kind of important that if dark matter isn't found in like this very small window, that we come up with new ways to constrain below this neutrino floor. Okay, so now I'll jump into the work that I've been doing over the past couple of years. And I'll first speak on the capture of dark matter. And this is essentially just a process in which dark matter particles become trapped in an astrophysical object like a star after colliding with the things in the star so that they get slow enough to get stuck, basically. So I'll first talk about the capture formalism if we just think of dark matter colliding with one type of nuclei in the object. So this is how it looks schematically. So we have a dark matter flux that is incident on some object. And essentially, every dark matter particle that is colliding with the object is going to have some probability of colliding, of interacting, basically, of scattering with the one component. And there's also, if it scatters a certain amount of times, which we're going to call n, there's a probability that it will become captured after that, or gravitationally bound. And this depends on how much energy is lost in each scatter. So in practice, this is how it looks. So we have the capture area of the object, which is just the area of a circle, because that's kind of what the dark matter will see as it's coming towards the object. We have the flux of dark matter, which depends on how dark matter is distributed around the in the neighborhood of the object, which is what this f function represents. And then, as I mentioned, we have this probability function for undergoing exactly n collisions, and this depends on this quantity called tau. And all this is what we call the optical depth, but it's just essentially the average number of scatters that dark matter is going to have as it passes through the object. So if it takes a path that goes straight through the center of the object, this is roughly, on average, how many times it's going to scatter off the stuff in the object. And then this represents the probability of being captured after scattering that amount of times. And notice there it depends on this u is the initial velocity of dark matter. So if it's going faster, obviously it will be harder to stop. So all of this gives what we call, everything inside this sum gives what we call the partial capture rate, which is the capture rate after exactly n scatters. And essentially, if we want to get the total capture rate in the object, we just sum this to infinity. In practice, we sum it till it's converged, but that's the idea, to get the total capture rate. Sorry, just give me 1 second. Okay, so here I wanted to just talk a little bit about the probability functions, along with some brief justifications. So the probability that dark matter undergoes n collisions is given by this function, which looks a little confusing at first, but I kind of want to walk through it visually to explain what's happening. Let's see. So if we have a dark matter particle, let's say that it's going pretty much head on to the object, and it's gonna sort of has a trajectory so that it would pass straight through the object. Then and let's say that this object is such that the average number of scatters if it goes through the center is 3. So if it's coming head on and the average number of scatters is 3, then we're expecting really that it's gonna scatter about 3 times, all right? And so the probability of having a certain amount of collisions is given by a Poisson distribution where we're putting in this just this 3 because we're going straight through the center. And so the idea is that if the particle comes straight in, it has a longer path and we get to access the full optical depth in a way. But if we had a particle, for example, that was coming in at some angle, right? In this case, it's going through it's going to pass through at a shorter path, right? So the optical depth essentially has to be reduced in a sense. And so what goes into the Poisson distribution here is sort of this effective optical depth, which is less. And that's just because the dark matter particle is seeing less of the object, right? So it's going to, on average, collide less times. And so back to this function here, the y represents exactly the cosine of that angle, which is what we mentioned. And essentially, all we're saying is, if dark matter is going to collide with this object, if that's what we know for certain, then the probability of it colliding a certain amount of scattering a certain amount of times with the different constituents, we have to add up all the possibilities from the different angles. So, right, so as I said, all we know is that it's going to collide with the object. Then we have to consider all the different angles at which it could be entering in order to figure out how likely it is to scatter a certain amount of times. And then now the probability of being captured after a certain amount of scatters. In the full form, it is a little daunting because you have to integrate over all the different possible angles at which the dark matter could scatter at, which is essentially the same as figuring out how much energy is being lost in each scatter. But if you make the assumption where you take the average energy that's being lost per scatter, you can kind of simplify this. So that's what we end up doing in the formalism. So we're saying essentially that dark matter collides n times, and each time it loses on average a certain amount of energy. And so how likely is it to get captured after colliding n times? Okay, so now before going to like a generalized case where we consider like a bunch of different scattering targets, we'll just go from a single component object to a two component first. And so the first thing that we do, or the first thing, one way that we can do it is by redefining what we're calling the partial capture rate. So we have to redefine it to account for all the different ways that n scatters can happen if we have two different components. So we're going to consider, we're going to let I be the number of scatters with a component that we call A, and J the number of scatters with a component that we call B. So it turns out that if I know that dark matter has collided or scattered n times, then there are n+1 different ways that this can happen. And a simple example to think about this is if I say dark matter scatters 2 different times, well, it could either both be with A. It could scatter off A, then scatter off A again, or it could scatter off A, then scatter off B, or it could scatter off B twice. That's 3 different ways. And so this partial capture rate itself becomes a sum, because you have to add up all the different ways that that could happen. And then the probability function also has to change, because now you have to think about essentially how much, so remember this optical depth that we talked about, this tau, sort of gives the average number of scatters, but now we have to think about the average number of scatters with A, and so the probability of scattering I times depends on that, and the probability of scattering J times with B depends on average how many times it would scatter with B. And then after that, if we look at the probability of being captured, it's now just based on what you've collided with. Because if you collide, for example, 2 times with A, and A is the heavier thing, you're more likely to get captured. So we have to adjust to consider for that. So it turns out that adjusting these probability functions are essentially the same, and the only sort of difference is this kind of imposition. So this second line here basically in plain English reads that if the component is not in the object, so for example, if we have a star that's made only of hydrogen and A represented helium, then we're saying, oh, if helium is not in the star, then we are not going to collide at all with helium, is essentially all this is saying, which makes sense. And it might seem like a sort of like false imposition, but if you like look at how this top function behaves as you send tau to 0, it turns out that it goes to 0. So this is just sort of a continuation of the top function. The probability of being captured now after I scatters with A and J scatters with B looks very similar to the N1, except now we integrate over all the energy lost in A and then over the energy lost in B. And once again, we're just going to take averages. So if I know it scatters I times with A, J times with B, then each time we're going to say, okay, on average, it loses about this amount, and then go from there. I just wanted to mention sort of an alternate way to interpret this. In some ways, this is more natural, and that is to forget about defining the partial capture rate as Cn, but just give it two indices, sorry. And then the function looks pretty much exactly the same as before, and we just double sum it, which is, they're completely equivalent. And I can actually show that with this graph here. So the original way that we thought about it was as though we're traveling along these blue lines, or I should say, the y-axis here is the number of scatters with hydrogen, and the x-axis is the number of scatters with helium. And essentially, each box represents some capture rate for a very specific scenario. So for example, this little box here is saying, I scattered once with hydrogen, twice with helium. What is the rate at which that's happening? And what is the capture rate associated with that specific event? And so to get the total capture rate, we're really just adding these squares. The original method was to add along these diagonals. And if you notice, the total number of scatters stays constant along these diagonals. So here we have 4 and 0, that's 4. 3 and 1, that's 4. 2 and 2, that's 4, etc. And so that's the idea before, where we said the partial capture rate is Cn. And so the n here would be 4. And so we're summing along these diagonals. The more natural way is to just sum horizontally. And it turns out that even though it looks like we are adding more things if we go along the diagonal, if we go past the average number of scatters, which is what this green line and this red line represents, then the chances of any of that happening are so low that basically all the squares outside of this box are irrelevant. Okay, so with that in mind, moving to like a more general formalism for any amount of components is pretty straightforward. So we just, essentially, if we have component 1, 2, all the way to n, we can think of alpha scatters with the first one, beta scatters with the second, and keep going. And then we can define this partial capture rate as alpha scatters with the first component, beta scatters with the second, etc. And essentially, it looks pretty much the same. We still have the capture area. We have these probability functions that we're multiplying of scattering with the different components. We have the flux, and then the probability of being captured. And then to get the total capture rate, you would just have these n different sums. Okay, so now I want to talk about an application of the two-component formalism that we focused on, which was to population 3 stars. And these are the hypothetical first stars in the universe. So Pop3 stars, being the first generation of stars, formed out of pristine gas from Big Bang nucleosynthesis. And all this means is that when they formed, they were made up of roughly 25% helium and 75% hydrogen. So the first step is we have to figure out what the optical depth is for these different components, hydrogen and helium. And to do that, we're going to need the scattering cross sections. So it turns out that for hydrogen, it's pretty straightforward because it is essentially just the scattering cross section of the proton. But helium, on the other hand, is a little bit different. So it ends up being proportional to the proton cross section, but there's this large enhancement because of helium's additional mass. This factor right here, this F squared thing, is a little like suppression, so it wants to kind of decrease the scattering cross section depending on the energy. But for the energies of the collisions in population 3 stars, this is pretty negligible, so it's of order 1. So the result of this like enhancement in the scattering cross section is actually that for a given set of stellar parameters, in most cases, helium basically dominates in the optical depth. So in other words, dark matter is much more likely to collide with helium than hydrogen as it transits a star. And this is true if you have helium above the fraction of like 2%. And that's really just because of this like significant enhancement. And so the effect of this is sort of what we would expect. So in this plot on the y-axis, we have the total capture rate. And the different colors represent different masses for population 3 stars. And then on the x-axis, we have different possible masses of dark matter. The solid line here represents the total capture rate if we consider the realistic scenario where we set the amount of helium in the star to be 25%. And the dashed line we use for comparison is if we have a star that's only hydrogen, which isn't physically realistic, but it shows you essentially that neglecting helium means that you underpredict the capture rate. So for almost all of the cases here, you see that the solid line is above the corresponding dashed line in terms of color, right? And there's sort of two reasons for this. The main is the one that I mentioned before, which is that dark matter ends up just wanting to collide a lot more with helium, and that's because of the enhancements of the cross-section. And the second reason, which is just that helium has a larger mass. So in each collision, the dark matter particle of a given mass is going to lose more energy by hitting off helium. There is an interesting exception, which is this line where you notice that this region here, where you notice the dashed lines and the solid lines coincide. And if you notice, the difference between these two panels is the cross-section. So this cross-section is about 5 orders of magnitude bigger than this one. So this represents the scenario where dark matter is colliding a lot of times as it's passing through the star. And it turns out that in this case, that dark matter is so light in this region and scatters so many times that it doesn't matter the helium content. It's always going to be captured. And so this is what people call the geometric capture rate, because essentially all the dark matter that's coming through gets captured. Okay, so now I'm going to discuss how we can use these objects to place bounds on dark matter. So after being captured, one possible outcome for a dark matter particle is to annihilate into standard model particles. And this could provide a source of heat for a star and essentially increase its luminosity. There are a ton of particle physics models that you can use and analyze this phenomena. But for the WIMP window, we stick to WIMPs, and then for the higher mass, other thermal or non-thermal models that annihilate. Another possible fate of dark matter is evaporation. And this is sort of fundamentally the same process as capture. So the idea here is that if a dark matter particle is in the star, right, and it's gravitationally bound, after a while it will thermalize, and inevitably it's going to have to interact with the stellar components. And essentially the idea here is that if the stellar components are hot enough, right, it could bounce a dark matter particle such that it gains enough energy to leave the star again. And it actually turns out that for higher dark matter masses, you can pretty much ignore this process. It depends on the object, this transition region. But for most objects above like 1 GeV, you can pretty much ignore evaporation because the dark matter is so heavy that no amount of hitting it is going to kick it out the star. So an important question that we ask when we're studying this phenomena is how the number of particles in the star behaves as a function of time. And this is governed by this differential equation. So we have capture as a positive term, because obviously that's allowing dark matter to accumulate into the star. We have annihilation, because that gets rid of dark matter, and evaporation, which also gets rid of dark matter. As I said, for the higher masses, we can kind of ignore evaporation. But in the lower mass region, it does become relevant. So after a certain amount of time, you can show that for population 3 stars, that the number of particles in the star will actually become constant at a time scale that's less than the star's lifetime, which is important. Because essentially what that does is that it sets this to 0, and then we can calculate annihilation in terms of capture and evaporation if it's relevant. And so after equilibrium occurs, the annihilation rate, as I said, it just ends up equaling to the capture rate minus the evaporation rate. And then this additional luminosity source from annihilation ends up just being the rate of annihilation times the mass of the dark matter particle. And so what we have here is a way to relate the luminosity, which is an observable thing, or an additional luminosity to the star, in terms of some dark matter stuff. So like the mass of dark matter and the scattering cross-section. Now, any star that is in hydrostatic equilibrium is limited in its luminosity by what's known as the Eddington Luminosity. And essentially, we have this inequality here for population 3 stars. So we have the nuclear luminosity plus the dark matter luminosity, and we're saying that has to be less than the Eddington luminosity for the star to exist. Now, as we saw before, we can recast this dark matter luminosity in terms of dark matter parameters. And essentially, if we just solve this equation for those dark matter parameters, we end up with constraints. So if we have to make some assumptions on some of the properties of dark matter, most importantly, the density around the object, the density of dark matter around the object, because that isn't, for these stars, that isn't a very well-constrained thing. So we have to do some modeling to figure out what we think the density is going to be around this object. And that could lead to some variability. Okay, so now I'll show the bounds in the region of high mass. And this is for a 1,000 solar mass Pop3 star in a dark matter environment where the density ranges from 10 to the 13 to 10 to the 16 GeV per centimeter cube. Now, the really striking thing about this is that if we consider a 25% helium object compared to a pure hydrogen, that we end up with pretty significantly deeper bounds. And this is readily explained by the fact that the capture rate gets boosted when we consider scattering with helium. If the capture rate gets boosted, that means that the annihilation rate ends up increasing because we're in equilibrium, right? And so that means that there's a stronger luminosity from dark matter. And what that means is that all this basically additional parameter space that was unconstrained before, we now have to say actually dark matter can't be in that window, because if it was and we observe these stars, it wouldn't be possible because it would push the luminosity above the Eddington limit, and so the star wouldn't exist to begin with. So this is really a really cool result of this work. And essentially for the higher density environments, there's actually the possibility to constrain below the neutrino floor. And as I mentioned before, this is kind of a constraint for current direct detection experiments. So, okay, so now I'll just go on to some concluding thoughts. So the major takeaways, I think, of the presentation are that we've provided a new formalism for calculating dark matter capture when you want to think of it scattering off of different components. We've applied this to the first stars in the universe, and we showed that the capture rates are actually about an order of magnitude higher than if you were to ignore this effect. And exactingly, it allows for the possibility to constrain below the neutrino floor if these population 3 stars are observed. And just some stuff on future work. We'd like to apply the formalism to other objects, relax, some assumptions that are kind of deep-seated in the formalisms that have to do with how the different nuclei are distributed in the object, and maybe even implemented in different stellar evolution code to figure out directly how this might affect the evolution of these objects. And with that, I can turn to any questions.
Thank you so much, Caleb. So yeah, I want to remind everyone that if you have any questions, which I'm sure you do, you must have some questions, to put them in the Q&A and we'll have them answered. But in the meantime, I have my own question, which is, I guess it's very short, which is that how does this capture model dependent on a particular dark matter model? Like, how's it dependent on if you're thinking about axions, WIMPs, machos, primordial black holes, whatever you're thinking of?
Yeah, that's a good question. So this is even true for the the single component formalism. The main input into the formalism is the scattering cross section. So it kind of I guess ignores in a sense what's happening on that level and is just taking like the cross section. So it's sort of like doing it in a model dependent way, I guess.
Cool, thank you.
Thanks for the question.
Okay, while we're waiting for more questions, I am curious about one thing that's not immediately tied to physics, which is what kind of jazz are you learning?
So now so I only just started like this semester, so I'm kind of just going through like some very old standards now, like it's like very like classic stuff like Body and Soul and In a Sentimental Mood, and I'm just kind of trying to wrap my head around like the harmony and how many chords there are, and yeah. I mean, I listen to a lot of like more like modern stuff, but I don't think I'm quite ready to like tackle that yet. So I'm sticking to like the classic stuff right now.
All right, well, if we don't have any more questions, I'll be keeping an eye out if we do. I want to thank you so much, Caleb, for your talk. It was really, really interesting. I've been in my fair share of dark matter and phenomenology talks, and it's not exactly my cup of tea, but I've always been really interested in and thought, man, if only I were in that field. But it looks like Farah does have a non-physics question as well.
I guess it is kind of physics related. So you mentioned you're from Jamaica.
Yes.
Yay, fellow Jamaican. Yeah, I guess I was curious to know how and when you got interested in dark matter research. I know for me, like, I didn't really know about many areas of physics research until I moved outside of Jamaica. But I went to school in like St. Elizabeth, so I know that like maybe you had that exposure in Kingston. I was just curious.
Yeah, I think I had like pretty much the same experience. I found that like the curriculum back home was very like tailored in a specific way. So like I took a gap year and I went to UWI and spoke to some of the professors there, some of the physics professors there, trying to like figure out if I could like get an internship. But nobody, I don't think anyone there was really doing any kind of theory physics. No talk of dark matter. It was mostly like climate stuff and like material science and like nuclear physics. So I didn't really, I only kind of knew about like dark matter and stuff from like pop physics. It wasn't until like I came to Colgate and started doing this research that I kind of like got a good understanding of the research. Back home, the path is kind of pretty tailored, I think. I don't know. I don't know if you feel the same way.
No, yeah, that's literally my experience. I tell people all the time that it's mostly like climate research and nuclear physics and not actually really nuclear physics. But did you get interested then in like your first couple years? I guess you're only a junior now.
Yeah, it was actually what like kind of triggered it was there was a talk by I don't know if you know Catherine Freest. She's like a dark matter theorist, cosmologist, and she was a advisor of my current advisor, Professor Ilie. And so she came to Colgate and gave a talk, and I remember going and I was like, oh wow, like this is really interesting. And so I reached out to Professor Ilie like as a freshman asking about it, and he was very nice, and you know I would go and speak to him about like this kind of stuff, and Then the next summer, I did research. I ended up doing research with him, and that's when I got like fully immersed.
Cool. Thanks for sharing with us. I definitely have a very similar experience that we can talk offline about. But thank you for your presentation, for answering the questions.
Thank you. Thanks for the questions.
All right. So I think, let me make sure I'm updated with chat. I think we're gonna close it out now. I want to thank you again, Caleb. Thank you, everyone on the panel. Thank you, Farah, for helping us out to organize this and really doing a lot of the organizing. To Lisa and Alina and everyone at KITP putting this together on their end. And I want to, I guess, sort of announce that we're gonna give everybody a break for the holidays, but we're gonna be back for Innovate at the end of January is when we'll try to organize the next one. So yeah, thank you again, everyone. Thank you so much.